Hello, welcome. The way this rule comes about is you're having a conversation with people talking about property prices. At least that's all people my age talk about. And someone says, oh, there's this property that I saw doubled in value over the last 12 years. And then some economist goes, that means it's a 6% annual return. And you think, hang on, how did you work that out? And actually, it wasn't that difficult. All they did was 72 divided by 12. And that gave them 6. So the number of years was 12 and then 6 was the percent. And so this rule is really simple, but the maths behind it is a bit more complicated and I think worthwhile looking at. So that's what I'm going to do in this video. So let's just see what's going on with a calculator. Let's say you start with £100, just an amount of money, and you want to double that amount. And you're told that you've got, say, a 6% increase. So let's use that example, 6% increase. So what you do is you times it by 1.06, and that gives you 106. So we're using multipliers here, and that's after 1 year. And then after another year, you can just press equals again, and you do the same thing. So this is compound interest. And then after 3 years, get this, 4 years, 5, 6, 7, 8, 9, 10, 11, 12. And now we've got 200, or about 200, which is double what we started with. And it was indeed 12 years, like in that example. So you can do this the other way round, in fact. What about 12%? Let's see how long that takes to double in value. So again, let's start with 100 and times it by 1.12, an increase of 12%. So that's 1 year, 2 years, 3, 4, 5, 6. And let's just look at 7. So 6 was just below 200, but 7 is way above 220, so it's definitely 6. And again, 72 divided by 12 gives you 6. And so what this rule does is it lets you go from a percentage to the number of years, or number of iterations effectively, to get double your initial value. And you can do it for other values. So you could check, you can do things like 8%, and you'll find it takes 9 years. Or a 9% annual return will take 8 years. And then you can do some other ones. But let's now do this on paper and see what's going on in a bit more detail. So you've got, in the first example, let's just say, we had 100 times 1.06 to the power of 12 gave us 201, thereabouts, 0.2196, etc., etc. Doesn't matter really, it's about 200. But really what we're interested in is not so much the starting value of 100, but the fact that we are doubling in value. So if we divide this by 100, both sides, this is what we're really getting, that 1.06 to the power of 12 is 2.012 ... And so really what we're looking at is 1.06 to 12 is approximately 2. And then this is where the rule comes in. So 6 as a percent times 12 gives you 72. Now, it's worth saying that in that example above of 3%, you might not want to press equals 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 24 times or thereabouts. So there is a fast way of doing this, and let's just write it down and have a look. So 1.03 to the power of something, let's say n, is equal to 2. And what is that n? Well, if you haven't done this, don't worry, but by definition, this is just a logarithm, and it's log base 1.03 of 2. Alternatively, you could write this as log 2 over log 1.03 if you're using a calculator like this, which has just the log base 10 feature. But don't worry too much. This is just a faster way of doing it, and this will give you 23.4, and that is about 24. So this works quite well because 3 times 24 is 72. And we could work it out the other way around, I should mention this, and that is if you say, given it took 24 years to double, what was the percent? So this same example we just did, you could say x to the power of 24 equals 2. What's x? X is this multiplier we're looking for, and this is just a rule of powers, so it's just 2 to the power of 1 over 24. And if you work that out, you get 1.029. which is very close to 3% or 2.9%. So this rule holds up pretty well. And what we now want to look at is more mathematically what is actually going on. And let's see if we can derive something that shows this rule. So before we really start writing anything down, we've got to be careful, because if we wrote down x to the n equals 2, there's very little we can do with that. But actually, we can do slightly better than that and go back to this first example here, where we wrote down 1.06 to 12 is about 2. Because this 1 occurs in all these examples. The 1 is not that important. It's really the 6 here from the 6% times by the 12 that gives 72. So what we might do instead is split this up into 1 plus the percentage, because that will give us more options to do further manipulations. So let's start a new piece of paper and write down. Now, if you want to try and do this all on your own, that's fine, you can try, but don't worry, because this type of maths is slightly beyond what you'd be expected to do at school in terms of intuition and thinking of what to do. So I'll lead you through the steps. So what we've got here is a binomial expansion, 1 plus x to the n. In fact, it's in a very standard form that you can just look up or you might know. And so I'm not going to go through the derivation of this, but this is just 1 plus nx plus n minus 1 over 2 x squared plus ... And by ... I mean all the higher order terms involving x cubed, x to the 4, and so on. Now, the thing to realize is that this rule of 72 is not exact. It's not perfect, but it's pretty good. And with all these rules that are not precise, but they are helpful, there's some sort of approximation going on. And what we want to do here is not write out infinitely many terms. We want to know roughly what's going on and have something that we can deal with algebraically. So far we've got constant here, a linear term, a quadratic term, and if we keep going we'll get cubics, and that gets very difficult to solve. So if only we could just get rid of the rest of the terms, that would make it a bit easier. And it turns out that we can, because x is small, it's less than 1, and as you raise the power of x, it gets much, much smaller. So what we could really say on the side is that x to the n tends to 0 as n tends to infinity. So in other words, these get smaller and we can eventually just ignore them. And so when we do that, we discard these terms here. So we can say this. And so what we're left with is then an equation that is much more manageable in terms of the algebra. So we have n minus 1 over 2 x squared. And instead of saying equals, I'll put an approximate sign because it's not exact. Now we are in an approximation, and this is actually a second order approximation because this is a first order term and then x squared is a second order term. And let's just simplify what we can. I don't like having fractions, and I don't like having a 1 and a 2 here. So let's just simplify this. I'll multiply out the n, and I'll use an equal sign now, but remember that it was an approximate from earlier, an approximation from earlier. So here we go, we just get this. And now you need to stop and think, right, what are we actually trying to do here? We've just been playing around with algebra without really thinking about where we're going. And the rule itself was, if you've got a percentage, so x in this case, you do 72 divided by that, or something like that. It might be 72 divided by 100x, because x is actually a decimal, but it's something like 72 divided by x will give you n. In other words, we need to solve x in terms of n, or n in terms of x. And we've got a choice, and you can do either. So I'll start off by solving it for x in terms of n. It feels a bit more natural, that's what we're generally used to, and it's already written in that form pretty much, because n is really a coefficient of x, the way we've written it. So let's just solve it that way. We'll write it as a quadratic. So n squared minus n x squared, and then plus 2n x minus 2 equals 0. And now here there is another thing we can do, and I'll try and give you a hint first so you can think about it. And remember that x is small. X is less than 1. And as you raise the powers of x, they get smaller, they decay. So what could you do here that's related to that, that is almost the other way round? And the answer is you could consider n, and n is large. N is an integer. N is a large integer, like 24 or 12 or 6. If you square that, it gets very big compared to what it started as. And so if we're trying to continue along this route of approximating things to make it easier, what you could do is actually say, let's discard this n term here. We don't want to get rid of this n because that will really simplify it down too much, but we can get rid of this n and we've still got a quadratic that we can solve. So if we just write it as n squared x squared plus 2nx minus 2 is approximately 0, because this was quite an approximation, then we can now use the quadratic formula. So we get x is minus b, which is minus 2n, plus or minus the square root of, and now we're doing b squared, so I'll just write this down in brackets, minus 4ac. Now c is minus 2, let's just put it in brackets to make sure we get it right, over 2a. Now, let's just simplify this, so leave it alone, this bit, and then sort out this square root. So we've got 4n squared, I'll do this on the side, this is actually 4n squared plus 8n squared, which is really 12n squared. So let's just put 12n squared here. It's quite useful to do a bit of work on the side sometimes and then come back to the main equation, 2n squared. Now I'll assume you can do surds. This isn't about teaching you surds, but root 12 is just 2 root 3 and n. And then on the denominator, you've still got 2n squared. And now you can simplify it a bit more because you've got 2 in every term. So we can write this as minus n plus or minus root 3n over n squared. And we can keep going because we've got an n common factor everywhere. And so this is really minus 1 plus or minus root 3 over n. Okay, now this is looking more exciting. And plus or minus, so there are two solutions. And we don't really want the negative solution because x is a percentage. We're not looking at negative percentages. So let's choose the plus one. And so we really got that x in the end is approximately minus 1 plus root 3 over n. And if you just work out what that is, that number, minus 1 plus root 3, it's 0.732, so on and so on. 0.732, which is very close to 0.72, which is what the rule was. So let's just say this is 0.73 over n. Now that's pretty close to what the rule is, although the rule was 72. Now we need to slightly be careful here because x, don't forget, is a percentage, and a percentage is out of 100. So there is a factor of 100 involved here. So we could slightly tidy this up, and if we multiply both sides by 100, we get 100x is 73 over n. Now that looks a bit better because 100x is effectively what we're doing. When we have 6%, we don't do 0.06, we're looking at 6. And so 73 over n is very close to the rule. And actually, really what's going on is 73 has very few factors. In fact, 73 is a prime number. So it's not a good one to use. Obviously, for a rule, we want it to be easy to use. And 72 has lots of factors. 2, 3, 4, 6, 8, 9, all these numbers are factors. So 72, you can see why that was used as the rule. And in terms of the accuracy of it, it's very close to 73, so it's basically fine. And actually, if you do this a little bit more accurately, and if you don't make that approximation, you get a slightly different thing here. You get 73 over n plus a small constant. So because this is already an approximation, whether it's 73 or 72 doesn't really matter. The important thing is we've got something that shows the rule. Now, I want to go through the other way round, where we have that equation. I'll write it down again. So we have this, and we want to make n the subject and solve it in terms of x. The first thing I would do is just rewrite this so x is the coefficient, not n. So this is 2xn plus x squared n squared minus x squared n equals 2. Now that is a lot easier to deal with, I think. So we've got x squared n squared. So we're writing it now as a quadratic, so we go for the highest power of n squared. And then what have we got here? 2x minus x squared, lots of n, minus 2 equals 0. Now, this is a quadratic in terms of n. Now, I'm hoping that if you think about approximating things, you can do a similar thing to what we did last time. But this time, instead of saying n is large, we're going to go back to before and say x is small. So we can really discard this x squared here if we want to make it a lot easier for us. So let's discard this x squared, and then we get this. And now you'll note that this equation is actually the same as the equation we just had previously. If you look at this one here, that's literally the same as this one here. We've just written the x and the n in the other order. And so you could actually here not even bother doing the work because we've done the work, and literally just write down that n equals what we had before, but we're just switching the x and the n around. So, because it's by symmetry, effectively. So minus 1 plus root 3 over x, which is what we had before. Okay, so we get the same thing, which is that, n is 73 over 100x. Now, if you didn't make that extra approximation, I'll just show you what happens. And basically, this is what you get. And you keep this n. Let's say we're solving for x. And you use the quadratic formula involving this n squared minus n term. And it's fine. You can do that. It works out. And you simplify this. And you eventually get to here. And you still, at this stage, basically have to say, well, now we've got n squared and n appearing in the same term, so we still discard the n and get the same thing. So it does end up as exactly the same thing if you do this. You're going to have to make an approximation at some point. And if you do it the other way around, in the other way, then here's one I did earlier. This is a bit more messy, but you can see what it's like. You get this complete mess, really. Lots and lots of terms, and I've put ... but basically if you do the actual expansion, you can do all of this, but it's not really worth it. You end up getting the same thing to start with. I think the nice thing about this problem is it really bridges the gap between what you do at school and university. Often at school you're just given a method and you're just told, do this, do that, get an answer. And then at university you do approximations increasingly. So particularly in physics, you do it all the time, astrophysics, definitely. And of course in applied maths, you do a lot of approximating. Basically in every subject you approximate things because if you actually want to find out what's going on in a way that we can solve, then you end up approximating things. As it happened, I only came across this problem a few years ago when I was teaching a year 8 class, percentage changes. And I think we were doing compound interest. And I think I got them as a way of checking they knew what they were doing to do this exact thing where you work out how long does it take to double your initial value given a particular percentage. And there happened to be an economics teacher observing me, and when we went through the lesson afterwards, he just mentioned casually this 72 rule, and I had no idea. And the first thing I did after that was sit down in the office and work out what was going on. And so yeah, I don't know much about economics, but I quite like this problem, being able to get to the bottom of why this rule works. Anyway, I hope this was helpful, and see you next time.